All right. Now we'll start chapter 20, which is Unicast Routing. And as always, comment sections are open. Comment section are open. If I say anything wrong and you want to correct it or etc., mention the minute and the second and correct anything I say wrong. Or if you want to elaborate more, just feel free to do so. And all credits, as usual, belongs to the KFUPM University, so the slides won't be shared. Okay, let's start. The outline is an introduction and then routing algorithms and then unicast routing protocols. The general idea in unicast routing, a packet is routed hop by hop. All right, hop by hop from its source to its destination with the help of the forwarding table. The source host need no forwarding table. Also, the destination host need no forwarding table. Only the intermediates need the forwarding table. Only the routers that glue together the network on the internet need the forwarding table. Okay, least cost routing. So here he's explaining that it started as a weighted graph, and the goal was to find the least cost between any two nodes. Okay. In other words, the source router chooses a route to the destination router in such a way that the total cost for the route is the least cost among all possible routes. Okay. Here is the graphical representation for the routers. Okay, we represent them as nodes, and these are the weights of them. So in order to move from A to B, you will need the cost will be 2, and so on. It's called a weighted graph, and it's just another way to represent the internet. Okay. Here it's explaining if you start from each node, how it will cost in order to reach to any other nodes and to the G also. So here, if you started from B, it will be far away from G by 7, for example, and C by 5. If you started from E, you will reach B by 4 steps and A by 6 steps and so on for each one of the nodes. So just like you pick one node and you see the least route that cost you, and you will choose it for each other node. So the neighbors will be directly connected. Then you will try to find, like for each other node that's not directly connected, which one is the least cost. Is it from A to D, then E, or is it from A to B, then E, which is in this case, the second case, which is A to B, then E. You will count the weights and you will see for each path. You will do this for all nodes. This is the concept here. Okay. Routing algorithms, several routing algorithms have been designed. So just the difference between them, the way that they find the least cost and how they create the least cost tree. We will discuss the common algorithms in this section, which is the distant vector routing and link state and path vector. You can search for this Bellman-Ford equation in the internet for more details, but I guess it's not important. I didn't actually understand it, and I just skip it. Distant vector routing, which is the first type of routing, is to find the best route. So it creates its own least cost tree for each node. It gives simple information. It has about the immediate neighbors, so it's know the cost for each nodes that it's directly connected to it. Then the incompatible tree, which means the nodes that are not directly connected to the node that we're talking about, it will try to exchange between the immediate neighbors to make the tree more and more complete. So it will ask its direct neighbors to give them more information about the nodes that are far away from it. Okay. we can say that a distance vector routing is continuously tells all of the neighbor what to know about the whole internet. So this is the definition for the distance vector routing. Try to understand it and memorize it because there is other routing technique that looks similar to this. Here is an example as a tree and as the distance vector for node A. So here is, for example, when it's as a tree, as we saw it before, you will pick the least root to each node and you will put the weights upon each one of them. And if you want to mention it as a distance vector, it will look like this. You will mention all the nodes, and at the top you will mention the node that you are talking about. Then you will see above A you got 0, so you put 0 here. About B, from A to B you will cost 2, so you will put 2. From A to D you will cost 3, so you put 3. Then A to C, it will cost you 7. You will put 7, and so on for the rest of the distance vector. Okay. The first distance vector. Okay, this is the initial distance vector that each node creates. As we saw before, it tells you like the direct neighbors. It will immediately be put in the distance vector. So here 3, that it's connecting A to D. It's directly connected. So I have this information about the D. What about B? It's also directly connected, so I know the information of the B, which is 2, and of course the A, from because we are starting from A, it's 0, as we saw previously here. So then the other are set to infinity, which means that either it's cut, so the path is, has a problem, or it does not know uh, the weight of it, and this is the case in our example. So it can't know any information except for the direct nodes that it's connected to. So it will ask, then they will share. A will share its distance vector with B, and B will share its distance vector with A, and so on, so that A can know more about the direct connecting nodes that are connected to B. So if B shares its distance vector with A and vice versa, A then will know that, oh, to get from A to C, I need, like, for example, 7 steps and so on. Uh, yeah, in this example, yes, it's 7. Because what you will do, it's that in order to be for B to reach to C, it will need 5. It will cost it 5. Okay. Then, in order for A to reach to the C, you will add just the 2, and you will get 7, and so on. So this is the concept. Each node will create its distance vector about only its neighbors nodes, and then they will start to share between each other and vice versa, so that they get the full distance vector uh, at the end. So you won't find any missing values uh, or infinite values, as you can see here in the example. And here's when they share. So here is the old B distance vector, and here is the A. So now B is trying to get information from A about the nodes that it's not directly connected to B. So it will see, okay, I have information about 2, so I don't care what you have, A. I have also about myself, so I don't care. I have about the C, so I don't care, but I don't have about D. And you have vector A have information about D. So okay, I will get I will use this information in order for me to get the value for D. So it will take 3 and it will add to it 2, as you can see here, because the weight from A to B is 2. So in order for B to know the information about D, it will take the weight from A to D, then it will add 2, because it's the path from B to A, as you can see from the graph. So when it's add 2 to it, it will get at the end 5, as you can see here. Okay. So, or you can see here, okay, because at the end we will take this and put it here. Okay, so it add to it. Here it says, okay, if E, I know the information about it, I don't care about anything you have A. Here it says, oh, I don't have any information about this and about this. Oh, can you give me anything? Oh, and then it looks to A and sees that it also has no information, so it will just keep it as is. So the new distance vector of new B, after getting a copy from A, it will be look like this. everything the same, but the thing that was empty in B and A got it, it will just take it and add to it the weight that is missing, or the distance between the B or the weight between B and A. Now it will be now here after we have got it here, we will take it just here, okay, and we'll consider it alt B now, and we get the copy now from node E. Okay, now we will see the same thing. I know all of this information, so B don't care. It already have information about how to go from B to E and B to D, B to C, B to B, and B to A. So I won't ask anyone. I don't care about any other information. Okay, but here F and G, I don't have any information. So can you help me, E? He looks at E and sees like, oh, it has an information, so I will take it. So it's 2, but I won't take only just 2. I will take only also the distance between me and E. And if you look at here, it's 4. So I will add to it the 2. So you have the 2, and I will add 4. I will get the 6. Then it will ask for the G. Oh, and also E do not have any information, so I will keep it as is. Okay. So the latest version of B after getting a copy from A and E will be 2, 0, 5, 5, 4, and 6. And the G still unknown. But after it's got a copy from C and G and F and E, it will get a copy from everyone. At the end, it will know the value of the G. Okay. But here in the example, he just gave you a copy of A and E to show you how to calculate. So only the concept here is do not forget to add the distance between or the weight between the nodes after you get the new information about the node that is unknown in the distance vector that you are currently trying to fill. Okay. Uh, okay. To a node instability. I skipped it, but the concept here says that if you have what happens if you have a cut or a problem in your link, there will be a problem that you reach to an infinite at the end because of of a problem I will try to explain now. Here it's telling you that the true value is 1 here, and here it's 2 when everything is all right. After you get link fail, as you can see, the link here is getting cut or something. It got a problem. It's getting cut or anything else. So the value changed randomly to 16 somehow. Then of course you know that this router will tell its neighbor about the new weight. Okay, then it will get the copy like this. Here it's A and B, right? So B will give a copy to A will give a copy to B, and so on, in order to know the distances or the new weights between them. So now when I get a wrong or a wrong number or random number, now what it will happen? A uh, after A is updated by B. So here if B is 2, so A is 1. But here I got something wrong, so it's 16. But B, it will tell the A again, oh, I'm 2, so uh, you should be bigger than by 1, okay, or something. So it will get back to 3, and B is still 2, and it's still all right. But now, guess what? A will give a copy to B back, so it will tell him, oh, I'm 3 now, so you must increment yourself, you must be bigger. So 3 will remain the same. He will get the B will get the information. It says that, oh, I am 3 now, so you must be bigger, so you go to 4. And now B will give a copy to A, so it will be 4 and 5 and so on and so on until they reach a point where they reach the infinity. They reach the infinity usually when the count is 15, I guess, or 16. So when they reach this number, they will get to the infinity, which means that they will keep updating each other. These dots remain, meaning that they will do this process the same for many times. At the end, they will get the infinity. They will assume that, oh, the link is got some problem, or or the value of it's unknown. Yeah, so this is just the concept. Link state routing, the second routing, it's also creating list tree and forwarding table. Link state. This method uses the term link state to define the character of the link and edge that represent a network in the internet. Okay, this algorithm in this algorithm, the cost associated with an edge defines the state of the link. Okay, so there's a cost. Links with the lower cost are preferred, of course. always and everything. The lower cost are preferred to links with higher cost. If the cost of the link is infinity, it means that the link does not exist or has been broken. Okay, so he's explaining here the infinity sample. Example of a link state database. Okay, uh, this is what we mean by the link state database. We will have the weighted graph. The link state database will look something like this. So you will take every node and put it here, and also put it up, and then normally just see the distance. So from A to A, it's 0, of course. From A to B, from A to B is 2. Then you will say from A to C. Oh, I can't see it anyway, so it will be infinity. Then from A to D, it's directly connected, so I know it's 3. So I put 3. Then the rest are indirectly connected. So you will put infinity in this case. Okay, you will put infinity. And same for every one of them. You will see the B, it has direct connected to C and E and A. So you will have values for you will have 4 values. Then the rest will be infinity and so on. So this is the link state database. You will made it like this, and you can see that this line is zeros. All right. What else? Uh, Here is explaining the concept more. Link state created and sent out by each node to build. Yeah, here the same concept. Each one of them will create the table with the node and the cost that with the direct nodes that it has. Then everyone will share, as you can see, it will share the table with each node so that to get more information and to get the full table, you can say, for all the nodes. Okay, so same concept as the previous uh, routing algorithm. So here he's giving you the difference between the distance vector and link state vector. The distance vector, each router tells its neighbor what it knows about the whole internet, whereas in link state, each router tells the whole internet what it knows about its neighbors. I know it's like a little bit confusing, but just try to memorize it. Okay. Uh, Least cost tree. Here is the concept of Digicastra algorithm. The concept simply says that just choose the least node from the start point, and at the same time that has not been visited yet. Okay, so here is explaining the one step by step, but I will try to explain it from here. Let's say we start from node A. He asks you to start from node A for the Digicastra algorithm. You will say, okay, what is uh, the least cost that is near to me that and also I didn't visit. It will say 2, so the B. Okay, then you will ask yourself again, okay, from A, what is the least cost that has not been visited yet again? You will say 2 again, but you visited already, so just skip it. The rule is it's least and you have not been, you didn't visit yet, okay? So now you will visit D. Okay, now you have done B and D. Now you will ask yourself, the nearest one is E, okay, now? But what is the least route? If I go from A to B, then E, the cost will be 2 plus 4, and it will be 6, okay? But if I go from A to D, then E, the cost will be 3 plus 5, which is 8. So what is the least cost? The least cost is this path, okay? So we'll go from A to B to E, okay? So you will have it like this, from A to B, A to D, then A, B, E. So you visit E now, okay? So you visit 3 till now. Now you will ask yourself, you will try to visit either C or F, because all of these have been visited, okay? So you will have to, you will have, yes, you will have one path from here. So because this have been cut now, because we reached E by this path A B E. So we won't have another path from A D E because E is already being visited. So I will go from here A to B, then to C will cost me 7. 2 plus 5. Okay. But if I go from A to B to E, then to F, it will cost me 2 plus 2, it will cost me 8. So the least what? It's 7. So I will go now to C. From A to B to C. You will connect here, and that's it. Now what is the least? To get to an F from the up, like from here, the same path, A, B, C, then F, or A, B, E, then F. Now we will count. Uh, A to B 2, then 5, it's 7, then 4, so it's 11. To get from A to B to C to F, it will cost you 11. But what if from A to B to E, then to F, you will have 4, then another 4, which is 8, which is the least. So you will go from, in order to visit F, you will go from A to B to E, then to F. And now last one, G, same thing, do the same things, just count from the routes that you have here. He explains much better, I guess. So he visits A, B at the same time. Okay, it should be 2 steps, but he visits 2 times at one step. Then he visits E, then C, then what? Then he visited, yeah, the C, the E, the C, then the F, and that at the end the G. And notice that each time he, like when he reached E, he didn't need this link anymore, so he deleted it. Okay, to make the graph look much better and to not confuse yourself when you search for the next upcoming node and so on. Okay, so this is the Digicastra algorithm. The concept is simple, just pick the least cost and at the same time the node that you have not been you didn't visit yet. Okay. Okay, the path vector, the last type, both link state and distance vector routing are based on the least cost goal. Okay, however, there are instances where the goal is not the priority. This goal is not priority. Okay, for example, if you want the sender, you want to prevent its packets from going through. So these two does not achieve this goal. So you will need another type of routing algorithm, which is path vector. And it's the same thing, okay? Each one of them will create distance vector, then it will share between all the nodes in order to get the full distance vector uh, table. But it just looks the difference, like here, to go from B to D, to look like this, B, comma, D, and that's it. The rest are the same. Here is the same concept. In updating, we have the old C. I will say here, oh, I have also already an information how to go from C to B and C to C, and also how to go to D and E. So I don't care about any information about this in the B. Just give me an information about something that I don't know, which is here the A. Okay. So whenever you have a path vector, you will start always with the C, as you can notice here. Always start with the C, then comma, then pick whatever you got in the new copy or the neighbors. Okay, so you will have here C, comma, B, comma, A. Okay, so this is uh, the new vector. Same concept, just normal adding. Okay, there is no cost here, so there is no numbers. Just add the two distance vectors. Now you will take this old and you will make it here, and same thing, but here guess what, I have everything. I have all information. I can know, I know how to reach every node from C, so I don't care about this. I won't change anything, so this will be the same. Okay, uh same thing, it will be just normal adding, but here, since I know already every information or how to uh go from node C to every node, so I don't care about anything you give me here. I already know everything, so I don't care about the node. But if there is something here missing, like for example, say you have something missing here, you will just start with the C, the node that you are currently in, then comma, then whatever you have and correspond to the copy you are getting from your neighbors. This is for part 1. Now we will go for part 2. Uh, Unicast routing protocols. Okay, you can see its application for the routing algorithms that we have taken we have just taken. Okay, so we have 3 types: common protocols. Okay, yes, common protocols. You have the routing information protocol (RIP). It's based on the distance vector. You have the open shortest path first. It's based on the link state. You have the border gateway protocol, which is based on the path vector. So he's just here explaining that the internet is complex and etc. We don't care. The routing protocols, you have the intra-domain and inter-domain. Inter-domain, which means like you can say like communicating with different networks or entities and so on. You can think of it like this. But intra-domain is communicating with the same within the network. Yeah, so you can see intra-domain is internal. It's internal, and interdomain is external. When dealing with external, we will use path vector that are based on the PGP. Whenever we are talking in the internal basis, we will think of the distance vector that is based on rib, and the link state, or I'm sorry, the open short path first that's based on the link state, and so on. So the first one is the routing rib is the most widely intra-domain routing protocol. It's based on distance vector. Okay, we know that. So here and whenever he give you a system and ask you to count, in rib we always count each node as one. So let's say, for example, you have the forwarding table for R1. You will create just a table for R1 in order to show how R1 can transfer from a hop to hop, how much it will cost, and what are the routers that it will pass through, and so on. So we will take it for R1. Now from R1, you want to go to N1, so it will cost you 1. It will just cost you 1. So that's it. So no next router. I am the same router. I'm just going to my neighbors. Same thing for 2. N2, I will just need 1. It will cost me 1 and no next router because it's directly connecting to me. But now if I want to go to N3, it will cost me 2. Why? 1 for this, and then other one for this. So it will be 2. Another one for this. And now the next router, which means the router that I have to visit before I reach to the N3, it will be R2. Sometimes there is like maybe more than one router. You will mention the first router. Like here, assume you have R2 and beside it is R3. So you will have 2 routers in order to reach the N3. You will mention R2 because he said next router. So the next immediate router, you will just put it. So it will be R2 in this case, and the cost will be 2. Now, if I want to visit N4, it will be uh, 1, so also 1 for each one. So from R1 to reach to N4, it will be 1, 2, 3. So the cost will be 3, and the next router is still R2, although we have 2 routers. Why? As I said, you will mention only the first router because here is saying next router. He does not mention all the routers until you reach N4. He just telling you what is the next router from R1 in order to reach N4. So it will be R2. Okay, but if he says mention all the routers until you reach the N4, you will say okay, R2 and R3. Same thing apply for R2. The besides N2 and N3 will be 1. The rest N1 and N4 will be 2. The next router from this side will be R1 in order to reach N1. Here it will be R3 in order to reach N4, and so on for the R3 also. Example of the autonomous system using grep. So here the same thing, like take this R1. What is R1? This R1. So it will cost from N1 by 1 by 1 by 1. So if, all of them are 1. What about the R2? It will cost you here 1 and 1 and also here 1. So this is the direct ones. Now, after each router creates its own table, they will try to share their table to each other and vice versa in order to get the full complete forwarding table. Okay, so they will do this same concept as before. You have the old R1, which is here, which will cost its neighbor by 1111. So I will take it as this because I already know the information, but I don't know the information about N4 and N5. So it's new information. So I will take it. I will take these costs and the next routers also as is, and I will put them. Same thing here for R3. I know information about N4 and N6, but I don't know anything about N3, N4, N5. So in 4 I know actually, but in 5 and in 3 I don't know. So I will take them as is, R2 and cost 2. Yes, you can see it will cost me 2, and the next router is R2. So each node, as we said before, will give its forwarding table to each one another and apply the same concept that I told you. If you already have the information to know how to get to that node, so just skip it. Don't do anything like this here. He just puts them as is in the new table, but the new things we will take them as is. And if there is any like thing, just you will count the distance between them, and you will add sometimes. But here he already added, I guess. That's why we didn't add anything or change anything. We make them as is. You can read more about them, but I guess it's clear. Same thing here. Here is he telling you that this is the final routing table. So after each forwarding table is being shared between among all the nodes, this will be the final table. So everyone will know from N1 to N6 all the information. How can I reach each one of them, and so on. Performance of rep, updating message. It's a very simple format. Do not normally create traffic. The converge of rep, usually it's converges slowly. Okay, and in rep it's only allowed 15 hops as a maximum number. So whenever you get 16, as I said before, it will consider it as infinity. As in that example, where you have a cut, and I told you they will keep updating each other. So when they reach 16, uh, they will get to the infinity state. As we said before, this vector route is based on the concept. Okay. There is a failure or corruption, the problem will be propagated to all routers. So whenever there is a cut or something, all of the routers will know, because they are continuously sharing all of their forwarding table between each other. And this is for part 2. Now the final part 3, open shortest path first, intra-domain also, which mean internal, and based on the link state routing protocol. Each link can be assigned a weight. Okay, so we have a weight here based on the throughput. So the weights are based on the throughput, round trip, and reliability. I guess you won't be asked to calculate the weight. Okay, it will be given. So here it's not the case as previous in rep, like each one the neighbors is 1. No, here we have a weight, and the weight will be given like this: cost 5, cost 3, cost 4. So the same concept. Let's apply it. R1. I want to go from R1 to N1. It will cost me 4. That's right. If I want to go from R1 to N2, it will cost me 5. That's it. What if I want to go N3? I will add 5 plus 3. It will be 8. What is the next route? Here it was directly, but here, in order to reach N3, I need to move through the R2 router, and it's the next router. What about the in 4, I will add 5 plus 3 plus 4, you will get 12. What is the next router? It's R2. If he says mention all the routers, you will say R2, then R3 in order to reach N4. But what's the next? We are thinking about the next from the R1, okay? From the R1, it will be R2. Same for R2 and R3. You can apply the same concept. Like here for R2, it will be 3 and 5, 3 and 5. Here it will be 3 and 4, 7. The next router is R3. From the left side, in order to get here, you will have 4, 5, and 4. It will be 9. What is the next router is R1. Yes. So that's it, and you will keep doing this for all router. Also, router 3 here, you'll get the same thing. Uh, Now with the border gateway protocol, BGP. Uh, so it's the only inter-domain routing protocol, which mean it's the external that it can communicate between different subsystems. What they were called, I don't know. Like consider it as a different network, or it's just a subsystem. I guess they would call it subsystem. I forget the name. BG4 is based on the path vector, as we said before. It is designed to provide information about reachability of the network and the internet. And here is an example for it. Uh, this is the name for it, abbreviation AS. I forget what AS stand for, but just to know, like the interdomain PGP allow you to communicate between different AS, okay, from different AS. Autonomous system, I guess, or something like this. So how it will contact from this border node from here to here, it will contact with this AS1, will contact from AS3 with this line from R2 to R6 via the border, the BGP, okay, the external BGP, okay. So here you have more example about it. So he tells you here, yeah, autonomous system. Okay, the AS is autonomous system. So the BGP, its job to allow you to communicate between different autonomous system. So it's only the only interdomain protocol. Uh, so each router in each autonomous system know how to reach to a network that it's an own autonomous system, but it does not know how to reach the network in another autonomous system. So here we are talking about the external communication. So we will need to use the services of PGP. So first of all, it will instance a variation of PGP called external PGP. ePGP, the abbreviation, on each border router. Border router we mean by like this. This is border router. This is border router. This is border router because it's the only router. Border router. This is border router. Okay. Border router we mean it communicate with other autonomous systems. So it's like at the edge, and we use it to communicate with other autonomous system. So each one of them will have ePGB. Okay. So here we have ePGB, E, ePGB, ePGB, ePGB. Okay. On each border router, as we said. Then install the second variation of PGB in order to let these communicate with each other. Like this one communicate with this, communicate with this. How you are going to do this by the internal PGB, iPGB. So each one of them will have iPGB, but the border one will have iPGB to communicate with the autonomous system itself, and the ePGB in order to communicate with the other autonomous system that are outside. Uh, okay, this means that the border routers will be running three routing protocol. Intradomain. Intradomain, we mean it's either a RIP or OSPF. It's default, you will find it always. So the intradomain in order they communicate between each other, and also ePGB because it will communicate with another autonomous system, and iPGB in order to communicate in the same autonomous system as well. But the other routers will have only intradomain and iPGB, so they don't have the ePGB like this one here, for example, R8. It only have intradomain, so it only have RIP or OSPF, and the iPGB in order to communicate with the others, but it won't have the ePGB, the external PGB, because it's not communicating with the other autonomous system. So here we don't have like an arrow with other autonomous system. That's why it does not have the ePGB. Okay, so the border router have three things. What is it? Intradomain, ePGB, and iPGB. Anything other than the border routers will have only intradomain, which mean RIP or OSPF, and the iPGP. Here is an example. Simple example if you look at it. Like let's say here, or where is it? N1, N8 and N9. This N8 and N9. The next router is R5, okay, and it's autonomous system 2, okay. Here is just telling you eBGB external PGP session. This is how it looks, okay. And each one will know the information about the other autonomous system. So here it's telling you the first autonomous system has the next router is R1, and they have N1, N2, N3, N4. N1, N2, N3, N4, and the other autonomous system is called 2, which is this. It has 9 and 8, and the next router is 5, okay, and same for the rest. Here it's telling you about the concept of the iPGP, okay, and also at the same time ePGP. So here is they have communication iPGB, iPGB. So all of them will have the PGP in order to communicate with each other. But the external ones, the border routers, will have also, in addition to that, an external PGP, ePGP. Also, this will have ePGP, both of them. This will have also PEPGP, these two. And this that are numbered, it's called the IPGP, okay? And here it's telling you how to create the table for it. Like, let's say, for example, number 1, next router is R1. It's connecting to what? There is no numbering, but it's connecting to N8 and N9, which is external. So it will be for this autonomous system. As I remembered, yes, 8 and 9. And here it's telling you it's connecting from the first autonomous system, which is this, to the second autonomous system, which is this. Just look at it. I don't know. I don't care about these things, but just look at it and you will understand it. Here is the most important thing: is how to create the path table for R1. Okay, so here is telling you from autonomous system 1 to autonomous system 2, like this one, we will have N8 and N9, okay, and the next router is R5, okay, nothing new. And here from autonomous system 1 to autonomous system 3, so this and this, from here to here, we will have the next router is R2. And what are the networks? It's in 10, 11, 12, 10, 11, 12, and so on for the rest. R3, R4, and R5, R6, 7, 8, 9. Okay, and after you do all of these, you will try now to see the tables that are have missing value. I don't know, it's called the injection. I didn't understand, but I guess it's the same concept. They will try to share between each other in order to get the full table, I guess. So take a look at it. Just try to connect the figure with the tables and you will understand it. You will understand it. Okay. So that's it for chapter 20.